Come on in. All right, so right here we're going to talk about continuity. So continuity. So a function is considered continuous at a number a. This little parentheses, right? It's continuous at a. Is it the limit of a function as you go to a is equal to the function value at a? And if we say a function is continuous on an interval, if a function is continuous for every number in that interval. This also means the function has to be defined at a. So if something's not defined at a point, it's not continuous at that point. To be continuous at the endpoints, it means to be continuous at the left at a or continuous at the right at a. So this allows us to be continuous on a closed interval, right? Because we can say it runs into that point and ends there, right? And then so we can say it's continuous even at that point. And then from then onward, and then from here be closing into the right side, okay? We say a function is continuous. So we say a function is continuous on an interval if it is continuous at every number in that interval. A function is continuous if we skip on the interval part, if it's continuous in every point in its domain, okay? Graphically, we think about this as it's unbroken. In other words, you could draw the curve without picking up your pencil up on the paper or the screen, depends on what you're writing on, right? So let's look at this. So here we have our function here, which we've seen a couple times already. And so here we have our function. The function is discontinuous at 1, right? So here at 1, it's not continuous. Why? Because here, first of all, the function limit doesn't exist, right? This doesn't come into any certain number. And second of all, it's not even defined here, right? There is no function. There is no f. F of 1 does not exist, right? Oops. Does not exist, right? Actually, f of 1 technically doesn't exist, but it's not defined, right? It's undefined. And why is that? Because if I put in 1 here, I have something over 0, and we can't do that for a function. So f of 1 is undefined. We call this type of continuity an infinite discontinuity, because here the function goes to the infinity. So here it goes up to the infinities, goes down to infinities. And so technically, so not only is this not defined, but the limit as x approaches 1 in this case, right, of f of x does not exist, right? It doesn't exist in the sense that it goes off to infinity. And so we call this an infinite discontinuity. Now let's look up here at 3. So right here. So here at 3, this type of continuity is called removable. So removable discontinuity. And explain what's wrong with this. Well, here, f of 3 is also undefined, right? It's undefined. So here it's undefined, and so here, but the limit exists, right? This limit exists, right? The limit is as x goes to 3, that exists, and it looks like a half, right? It looks like a half right here. So that exists. However, the function itself is not defined. Well, let's pretend the function was defined. Let me do something really quick right here. Let's pretend we had some g of x, which also looks exactly like this, right? Where we say x is x minus 3 or x squared minus 4x plus 3 when x is not equal to 3. And let's just say it's 4 when x equals to 3. So if we had this here, oops, I'm on the wrong layer. Here, once again, we still have this hole, but now we're going to define the thing right here. So what's our problem now? The problem now is that, our limit's defined, but the limit here, the problem is I didn't leave myself room. I'll write it up here, I guess. The limit as x approaches 3 of f of x does not equal the function at 3. Okay? because here the limit's defined and it's a half, but the function here at 3 is 4, right? And so we still call this removable. So if it looks like this, where it's just a hole, we call that a removable. Or if it has a hole and it is defined with something up here, we call it removable. So these are the two removables, if it's a hole or if it's a hole with the thing with the actual point up, right? The infinites, when it comes up, it looks like this. Okay. All right. So I'll leave that for a second. Take a drink. And then we'll go to the next page. All right. Let's go on to the next page. So let's look at this. So here's the Heaviside function. And so here we'll define the Heaviside function this way. So we'll define it in the singular term. It's used in study for lectures. This is common. So this, and so here's just real quick. So it's just 0 and then turns on to 1. So this function is discontinuous at 0, right? The type of discontinuity, and this one's called a jump. We call this a jump discontinuity. And what the jump discontinuity means is that it's often that the limit of f of limit, in this case, we'll go ahead and say the 0. The limit of f of x is 0 plus is equal to 1. But that does not equal the limit of f of x as x goes to 0 minus, which in this case is 0. So here, if I come in from the left side, the limit of 0 to the approaching left, it looks like 0. If I come in from the right, it looks like 1. And so this limit doesn't exist. So the limit here doesn't exist. So the limit of f of x goes to 0 of f of x does not exist. And notice here, we'd call this a jump discontinuity. Even if our value was here and this was an open circle. So let me draw another example here in kind of blue. Let's just go here. And so we'd also call this a jump discontinuity. And we'd also would call something like here. If I came here and it jumped down here and I had the value up here. And so let's pretend this is one function. So as long as there is like a jump, but it looks continuous up to that point. And so these are the three kind of things you'll see for jump continuity. So where the actual value is doesn't matter as long as there's a jump right here. You'll get used to which one's which, and you'll have homework problems that will do that. All right, so let's identify these again. So right here, so we're going to find all of this. So identify which continuities at each one. So here we're going to find. So this is discontinuous at three points. So what are the three values this is discontinuous at? Let's put that in chat for me, just to make sure I know you guys are still alive. What 3 values is this function discontinuous at? See if anyone's awake. Okay, so -2 is one of them. So -2, -5 is another one, and 2. Yeah, so that's all of them. So here at -5, let's just do this in order. So at -5, what type of discontinuity is this? This is what type? And then we'll do at -2 and then at 2. So this one is jump removable. And so, yeah, so here, this makes it, I'm glad we went over this. So this here is a removable because for removable, the limit exists, right? For the removable, the limit exists, right? Here, the limit exists here. For removable, the limit exists. Okay, I'm gonna write that on our notes. Exist, right? The limit exists. Except it's not defined. The function value is not defined at that point, or it's in the sense that it's not that point, or it's not defined at all, or it's defined but it isn't the same as the limit. So this one is removable. Okay. Here at -2, what's happening? Yeah, this one's a jump, right? This one we're jumping, okay? So here's a jump discontinuity because it goes from one value and this instantly hops to another. And then here at +2, what type of discontinuity is this? Infinite, yeah. And so that's why I do a couple of these just to get you used to the vernacular. This is a jump, this is removable since it comes and there's a hole. This is a jump, and this is, so really what you're paying attention to, what your pencil does. So here, I just lift up my pencil for a second. Here, I jump with my pencil, and here I go off to infinity, right? So these are the three different types. All right, so I'm going to take a drink. We'll go to the next page. Could you move it over for a bit? So this would be another example, and this is another example. So treat these as separate. Okay. Okay, so let's go on to the next page. I can't see the left side. For the first page? Anyone else having troubles or just the one student? Okay, I do need to move on. Don't worry, these do get posted for later. All right, so let's do the next one. So here we have our theorem, and this is what we usually rely on 90% of the time. The following types of functions are continuous at every number in their domains. So polynomial functions, exponential functions, rational functions within their domains, right? Within their domain, logarithmic functions, root functions, and trigonometric functions. Okay, so all of these are, we call these elementary functions, right? And most things you know are elementary functions, and most of those are continuous within their domain. Okay, so let's just kind of go through this. So we're going to identify the domains of each of these functions. We're going to state whether each of the, and then we're going to state whether each of the, where each of, state the numbers and where each is discontinuous in the type. Okay, so this one, let's look at, and I'm just going to use D colon for domain. Our domain for x cubed is all real numbers, right? So from -infinity. Or you could just write all reals. Okay. Does this have any? And so there's no discontinuities. So there's no. And I'm just for my own. I'm just gonna discon. All right. So there's no discontinuities. I'll just put a little. Here, this is a rational function. So here we had a polynomial function. It's continuous everywhere in its domain. In fact, since its domain is everything, it's always continuous. So there's no point of discontinuity. Here, we're going to look at this one. We have 1 over x, and so this is a rational function. So the domain here is from -infinity to 0, not including the 0, and from 0 to infinity. So basically, the domain's everything here. Well, where's the point it's discontinuous? Well, it's discontinuous at 0, and it's an infinite. So infinite discontinuity. So we said, so here it's continuous everywhere in its domain. It's not continuous it's discontinuous at 0 or not continuous at 0, which is the one point outside its domain when this is an infinite type. Well, here we go. The domain of a square root function is from 0 to infinity. And where is discontinuous? It's nowhere discontinuous, right? In the sense that it's nowhere discontinuous outside of its domain. How could you say, is it discontinuous over here? It's like, well, neither the function nor the limits defined here. So technically, maybe you could say that. I don't, and we just don't deal with it, I guess, right? And so there's no real discontinuities because it's just plain not defined. And so if we're going to say, where is this continuous? Well, this is continuous on the interval from 0 to infinity. And the reason we can say 0 inclusive is because we can go here and saying it's continuous from the left, right? So as I'm walking in this way, oh, hold on. Did I draw these backwards? I might have drawn these backwards. If I'm coming in from the left, oops. If I'm coming in from the left, I hit a number here. I drew these backwards. My good old dyslexia. And here, if I'm coming in from the right, and here. So here we're coming in from the right. And then I'm here. And so here, if I look over, oops, there we go. Here's I'm coming in, if I'm coming into my function, right, from the right-hand side, I have a limit, and that limit looks like 0. And what's the actual function value? Well, the actual function value is 0. And so here we can say it is continuous at the point 0, because we can walk all the way up to that point, and it is defined as the right-hand side limit is equal to that point. And so we can say this. Okay? So if a function just abruptly stops and doesn't continue, you can say it is continuous at that point up to that point. And that's just, so it equals its domain. All right, so an exponential function. An exponential function is, anything of a to the x, right? And here we just have the natural log. Well, the exponential function is defined for the entire domain. So it's defined from minus infinity to infinity. And since it's defined everywhere, there's no discontinuities here. So there's no discontinuities. Okay. Here, our function here, log functions are defined between 0 to infinity, right? We can't have it equal to 0, but we can have everything up to 0. And notice this function is continuous. So there's no real discontinuities here, right? Even though this one kind of looks like an infinite discontinuities, but there's nothing on the other side. And so we just say the function's continuous from 0 to infinity. And there's no real defined discontinuity here. So let's look at the tangent function. It was asked that we do more of the trig stuff, and so here's at least one of them. I might do 1 or 2 examples on the side to help a trig if that's what you guys are struggling with. I'm happy to do that. All right, so here, what's the domain of this? What's the domain of tangent? Well, here it's everywhere except at pi over 2, 3 pi over 2, minus pi over 2. And so we say all real numbers except, and here we're going to have x, except for where x is equal to 2n plus 1 over pi over 2. Where n exists in the integers, right? And this means n is an element of the integers. And so this is just a way of saying, because when n is 0, this is 1, and I have pi over 2. So it's all real numbers except pi over 2. When n is 2, or when n is 1, this is 3 pi. This becomes 3, so this is 3 pi over 2. When n is negative 1, this becomes minus 2 plus 1, so it'll be minus 1. And so that gives us this. And so this is just a fancy way of drawing all these lines of discontinuity. Hopefully you've seen this before in your pre-calc class. If not, that's just, what is n equal to? Oh, n, let me write this in a little bit clear. This is, hopefully, if you guys don't know this, we'll go over this right now. N is an element of the integers, okay? So real quick, this means reals. This means the integers. This means rational numbers. This means the natural numbers, where it's just the extra line. Have you guys seen all these before? Yes, yes, no. Oh, okay. Oh boy. So let me just, let's pause for 2 seconds then and write it down. So this is the real numbers, okay? This is the rational numbers. This is the integers. It comes from German, I think, for integer. And this are the natural numbers. And I guess the only other ones you might need to know is the C with an extra line in it are complex numbers. Okay. And so this is just a way of saying all real numbers. So right here, the reals, right? All real numbers are from negative infinity to infinity. All rational numbers, so that means numbers you can write as one over another. Integers are negative 0, 1, 2, 3, 4, and -1, -2, -3. Natural numbers start at 1, so 1, 2, 3, and 4. And complex numbers or anything. So here, when we say n is an element of the integers, what I'm saying here is n can be any. So it's all real numbers except where n, except where n is equal to this. Or so n can be 1, 2, -5, -20, but it can't be -2.5. Okay, and so this is just a way of saying the domain here. Okay, because you have in trig you have to skip a lot of things for like the tangent functions. It just becomes undefined at a lot of points, and so this is not defined anywhere. Now, is it continuous everywhere in its domain? Yeah, it's continuous everywhere except at these points. Now, where is it continuous? Well, at these points. It's discontinuous at these points, and the type of discontinuity is infinite, right? Because here it comes from positive infinity to negative infinity. So here, let's just look at this line right here. Here we have our infinite discontinuity, okay? All right. So let me go ahead and save the first 3 pages real quick. And then we'll shut them down because it's getting a teeny bit crunchy. And about 3 pages in, it says, no, don't do that to me. That's fine. Don't save. I'll export this one. Thinks about it. That's not what I told you to do. That's what I told you to do, not what I wanted to do. All right. Let's go ahead and export it just a quick PNG for me. Thank you. Whoop. Nice. And then we'll export this one also as a quick PNG real quick. Okay. I have it later as a reference, and if I need to pull it up, I can show you. All right, let's look at this one. All right, so one of the questions we like to do is how do we want to make things continuous? So determine what value of k will make this function continuous. So let's look at this function real quick. Let's just kind of, let's go ahead and look at this function. So let's go ahead and just roughly draw it. So here at up to 2, it's 1, 2, 3, 4, 5. So -5, and we go up 3, so 1. And so here I'll have 1, 2, 3, and over 1, and then 1, 2, 3, and over 1. And so this is at 2. And so I have something that vaguely looks like this. But from 2 on, it doesn't equal this, right? Oops, I'm on the wrong layer. And so I want to match this up. So here I have something that's kind of going down at a -2 slope, right? But I want to match it up so that these make this continuous. And so here we're just going to find out what the value of 2 is at, right? I need to know what the value of g of 2 is at. Well, here I'm going to be using this, right? Well, g of 2 is equal to 3 times 2 minus 5, which is equal to, so 6 minus 5 is equal to 1, okay? And here our graph shows the same, right? Here's a graph that our graph shows the same when we did it. Now, I want the limit. So the limit of, so here, real quick, I ask you, what's the limit as x goes to 2 from the negative side, right? Or from the left of g of x. What is that limit? Well, here it's just going to be this, right? Here I'm walking in this way, so also it's also going to be 1. So what do I want? I also want the limit of x goes from 2 to the positive side of g of x to equal 1. Well, how do I do that? Well, I'm going to make this, I'm going to set this equal to 1 when x is 2, right? Since this is a line, we can just set that equal to, when x is 2, we'll set this equal to 1. So if I solve for that, that becomes minus 4 plus k is equal to 1. I mean, k is equal to 5. So there's our answer, what value of k. And let's just graph this in real quick. So 1, 2, 3, 4, 5. And we go over 1, down 2, and then over 1, down 2. And then here we have our line, and it just continues on from here. Okay? So if we set k equal to 5, we'll get this graph. Does everyone understand my logic in doing this? Often you'll see piecewise functions in these homeworks and stuff where it says what value makes this continuous, and you choose a value in which, as it approaches from the right, equals the value when it approaches from the left. Could you write out those steps or repeat them? Oh, how did you graph it again? They're just lines. They're just lines. So here, this is my intercept. So x minus 5, and then I go up 1, 2, 3, and so I go up 3 and over 1, up 3 and over 1, right? And here, when I graph this line in, I started at 5 because that's what k is, and I went down. I went over 1, down 2, so over 1, down 2, over 1, over 1, down 2. Just how I graphed it. Yeah, so k is 5. But, oh, no, yeah. So here, if I put this back in, k is 5, and then this one turns into plus 5. So here, this is minus 5. Just when I was graphing it. When you graph this line, here we get that. I'm going to graph this line. And so the steps to solve this is we want to find, let me see if I can write out some steps for you real quick. So the steps to solve this is you want, what do we want? So we want the limit as x approaches a to equal the limit as x approaches a minus, and we want that to equal the function value. Okay, so here we want all these three things to equal. In our case, the limit, and so in our case, this and this are the same because they come from this function, right? And since this is a and so both of these were 1. And so we also wanted the limit from the right-hand side to equal 1. Well, the limit from the right-hand side to equal 1, well, g of x from the right side is now this, right? Because here we're coming in from values greater than it. And so we set that equal to 1 and solve. Okay? Hopefully that makes sense. All right. So let me zoom out as I talk about the last little bit right here. So if f and g are continuous at a and c is a constant, then the following functions are also continuous at a. So you can add two functions and they'll still be continuous. You can multiply by a constant, that'll still be continuous. You can minus two functions and that'll be continuous. You can multiply by a constant, or you can just multiply the function together, that would be continuous. And then you can divide the two functions as long as the value you're looking at is not 0. Then if g is continuous at a and f is continuous at g of a, then the composite also is continuous. And so this, between these and this statement, most of the stuff you can just prove is continuous using that, right? So if I had like the sine of x squared, right? Well, this is continuous everywhere in its domain. So this, in this case, it'd be my g G is continuous at A. Well, G, this is my G, right? For my function composition, right? This is continuous everywhere. And therefore, this is and sine of x is continuous everywhere. Because notice sine of x is just one of the trig functions whose domain is all real numbers. And so it's continuous everywhere. And so this is continuous everywhere, even though it's not strictly listed above. And so you can use this composite function, use it to get most of your things are continuous, right? And so as long as everything's, it's in its domain in that. So you can use this theorem a lot along with this theorem, or the theorem that before it says polynomial rational function exponential are continuous in the domain. All right, so all this continuity stuff produces a nice little theorem for us, which we call here. And so here we call this the immediate value theorem. And so suppose as f is continuous on a closed interval from a to b, and let n be any number between f of a to f of b, where f of a does not equal f of b. Okay, if f of a equals f of b, it gets a little bit. Then there exists a number c in this interval such that f of c equals n. And what's that really saying? So let me show you this here. So we're going to use this immediate value theorem to show there is a root of the equation between 1 and 2. Now, what does a root mean? It means something. It means if I plug in that value, I'm going to get 0 back, right? And so here we're going to let f of x equal the following. So we're going to let f of x equal this. That way we just have something to plug into. Oops, make that look like a plus. Hi. Notice on your notes, you may not have the 6 here. That was corrected. But if it's not there, just write 6 real quick. All right, so here, what's the function value at 1? Well, the function value at 1, well, this is just 4. Hold on, I don't want to be. I'll make sure I have this all up. Okay, so I have 4 minus 6 plus 3 minus 2. Notice here if x is 1, this just ends up being 1. And so that's equal to minus 1. What's the function value here at 2? Is this function continuous everywhere? I just label this, not the equation, but the function f of x. Is this continuous everywhere? The answer is yes, it's a polynomial, right? So this is continuous everywhere. So we're safely can apply the intermediate value theorem. So here at 2, the values here you get a 32 minus 24 plus 6 minus 2. And if I plug that all in, I'm going to get 12. But notice here, and so what does a root mean? A root means f of x is equal to 0, right? That's what a root means, right? If there's a root of this equation, that means this part, if I plug in some x, I'm going to get a 0 out, right? And that means 0 equals 0. And so I want to find that. But notice that this is less than 0, right? This right here is less than 0. And then yet I'm above it, this is greater than 0. That means somewhere in between 1 and 2, according to the intermediate value theorem, there must be an f of c such that equals 0, right? Because some n is some number between f of a. Notice f of a here is -1, and f of b here is 12. So there's some number n. Notice zeros between -1 and 12. Where c exists in the interval between 1 and 2, right? Because that's a and b. So here's our a and b. And let's show this graphically. So here we can say, yes, it exists by the intermediate value theorem. Since this is below 1, this is above. So here we've shown our condition. And so -1 is less than 0, which is less than 12, right? So it's in between these numbers, right? So therefore, we can apply the theorem. Let me just show you in Desmos real quick, and then we'll be done with the notes. All right, Desmos. Here I can kind of explain graphically. It's kind of like a squeeze in a sense. Yeah, a little bit, right? All right, let's open up Desmos. So here we have 4x cubed minus 6x squared. Was it plus 3x plus minus 2? Was that my function? Double check. Yes, that's my function. All right, so let's look right here. So here we have a number at 1, -1, right? So we found this. So between here and then 2, notice that 2 should be, let's see if I can get it to land. Yeah, 2, it's 12, right? And so we're saying between here and here, there has to be a 0, right? And the 0 is an answer. Now, where's the 0 at? Well, it's some weird number, right? And this is still an approximation. So it's not some odd number, but we know there is a root between here and here, just because I know that this is negative and this is positive. And we use the intermediate volume theorem a lot to find roots. Because if we know if the number goes from positive to negative or negative to positive, that means there's a 0 in between. And so when computers actually calculate the numbers, they kind of just like guess where they're at. If it's not nice, right? It'll just guess where it's at. And then if it's positive or negative, it's like, okay. And it'll keep walking those numbers in until it kind of crunches on it. And so that's how the computer does it. But we won't do numerical methods in this class. But yeah, it kind of squeezes in. It says, okay, it's negative here, it's positive here. And then it just keeps walking towards those two numbers until one of them gets really close to 0. So that's kind of how it goes. All right, so that's the end of these notes. So we'll go ahead and